record to, yeah, we're gonna record to the cloud. That'll be better because my computer might. Yeah, we're gonna go over Kaidi's practice midterms. Yeah, and I might go over some extra content. So if you're already comfortable with Kaidi's practice midterms, then you can, I guess, you don't need to. I mean, you can stay if you want, but like if you're already comfortable, you don't feel like you need to be here. Please no donut, no Helmholtz. Yeah, I'm not gonna cover quantum physics or topological manifolds. Don't worry, it's gonna be purely linear algebra focused. We're gonna go over the practice questions and we're gonna go slowly through them just to make sure everybody understands the content. And I'll make sure if there's like definitions that we're gonna use, I will go over them. So don't worry about that. Kaidi's scared of donuts. Yeah, I'm not gonna cover toruses. They're not relevant to any of the proofs we're doing. So, I mean, I'm not gonna cover that, even though I'm very interested in that stuff. But I mean, this isn't about topology or manifolds, so we're not gonna cover that. Yeah, well, yeah, no, this is gonna be on our practice midterm. I have slides on all the questions. So, or have I seen your midterm? No, I haven't. I haven't seen your actual midterm. Can we go over eigenvalues and vectors in depth? Well, I mean, we're going to be going over proofs of eigenvectors and vectors. So, I mean, how I'm going to sort of handle this is we're going to go over, yes, this is being recorded. So how I'm going to, there's 3 people waiting. Okay. Is there like an option on Zoom to just admit anyone automatically who joins? Turn off, wait, oh, okay. How do you, because I don't want people, I don't want people like stuck in the waiting room. So security. Yeah, we're just gonna do that before I start, just so people aren't like hanging around in the waiting room. Where is the waiting room? Where is it? Oh, here we go. Yeah, okay. No waiting room. Okay, great. So now everyone can just join. And hopefully this recording, great. Okay. What time is it? Okay, we'll take 2 more minutes in case some people need to get here. And then we can start. Yay, linear algebra. Very nice subject. So we're gonna have a good time tonight and we're gonna go over some fun questions and yeah, just have a good time. Is linear algebra 2 mandatory for CS? It depends on whether you're doing specialist or major. If you're doing major, then technically no, but it is a prerequisite for like a few courses, so just be aware of that. But no, you either take one of STAB 52 or MATA22. But if you're doing the specialist, you do have to take linear algebra 2. So it depends. But it's really not that bad if you can get through linear algebra 1. Linear algebra 2 is mostly review. From what I remember, I think the first half of the course was just review. I think it's all of the specialists have it mandatory. Right, okay. Okay, I mean, it's 7:10, so I'm assuming everybody's here. I'm just gonna text my friend Haylin quickly in case the room reaches capacity. If seminar capacity stream. Okay, fantastic. All right, we're gonna get started because I'm sure everyone's sick of waiting by now. So let's cut through all this and let's get started. So everyone's good with starting, right? Nobody's against starting. We're good. Everyone's good to start? Okay. Right. All right. So welcome to the AMAC MATA22 term test review seminar. We're going to be going over the questions on the practice midterm, not including question 7 because I thought it was like a little easy and I got lazy, so I didn't want to do it. So, but everything else will be covered. So without further ado, let's get into it. right? So first question, prove that for all complex numbers in the complex, like for all numbers in the complex plane, right, we have the modulus of the complex number is less than or equal to its real part plus its imaginary part, which is less than or equal to square root of 2 times its modulus. All right, so I mean, I'm sure a lot of you are looking at this and going, wow, that looks like a lot, right? Well, we need to, let's break it into parts, right? Because when you're sort of doing proofs, you like to just take it slow, see what you have, and see what you can do in parts, right? Because you don't want to bite off the whole, you don't want to bite into like the whole sandwich. You want to take a little bite here, a little bite there, and try to sort of work out, right, how you want to go about it. So, right, so we're going to prove this lemma, right? We have, which is, well, we can sort of see it's like this part of the inequality, right? Because it's much easier to do it in two parts than to like try to do it all at once, because if you're doing it all at once, it's kind of hard to keep track of everything. So it's good that we can sort of prove it this way, right? So great. Lemma, oh yeah, so when I say lemma, I just mean like intermediary proof. It's basically it's the same thing as proving like a theorem, but we use lemma to sort of like denote that it's an intermediary. Basically, it's something that we use to get to the result, right? So this is just this part, right? We're just breaking it into parts. But anyways, right, so we're going to recall our definitions, right? A complex number can be written as a real part and an imaginary part, and the real, both parts, or both of the values, right? The real value and the imaginary value are in R, right? Except for the actual imaginary component, right? So you can almost sort of think of these as like somehow analogous to two-dimensional vectors. The only thing that's different is the multiplication rule with the imaginary component, but you can kind of think of this as, right, vector in R2, right? Or sort of anyways. You'll make that more formal later on, but if you're confused about like what these sort of are, like that's how you can sort of think about them. So yeah. Okay, so we know that the real part is the A part, and the imaginary part is the B part, right? So if we look at the definitions, right, of the modulus, so you probably recall that the modulus, right, of the complex number, just the real part squared plus the imaginary part squared, and then you take the square root of that. So yeah, so this is just this. Is that clear? Everyone knows that, right? We're clear with that. And obviously, well, we know that the real part is just A, the imaginary part is just B. So, right, we have these two are sort of, right, analogous. So just so we're clear on our definitions, because that's really important. What was the lemma again? Okay, yeah, sure. Give me 1 second. Right, so the lemma is just this, right? So this is the first half part of our proof, right? So we have this part, right? We're trying to prove this part, and then after we're going to go ahead and prove the other half. So that's sort of our lemma, right? Yeah, so we might recall, well, if we have an inequality, yeah, so what is MZ? MZ is the imaginary part, right? So you have I right here, right? And you have B right here. So you have that's your imaginary part, right? So that's the second half of the complex number. So the imaginary part is just the real number that's multiplied, I guess you could think of it like by your imaginary component, right? So you'd have A plus IB, and B is your imaginary component. Yeah, so I know everyone probably has more questions, but I'm gonna try to get through this more because I wanna make decent time. So I guess I'll answer more questions later, but yeah, I do appreciate all your questions, so thanks. So you'll recall, right, if both sides of an inequality are positive, well, then we can square both sides and still preserve our inequality, right? Because positive thing times positive thing, that's a positive thing. And then another positive thing times positive thing, that's a positive thing, right? So we have this sort of if and only if relation, right? Because you can square this and, well, that will be the absolute value of this, but that's positive. So we can remove the absolute value and vice versa, right? We can square both sides and you'll get this. So it's very important that we know that this is sort of equivalent, right? So these these two are sort of equivalent, right? So there's sort of a back and forth relation, right? So that's really nice because we can sort of prove this, which is much easier to show, right? So a lot of the times in proofs, you'll use these sort of if and only if relations with inequalities and equalities to sort of show what you want, right? So we're going to note that, oh, well, squaring the square root is just undoing the square root, right? That's pretty clear, right? And oh, well, we also know that the absolute value of a squared plus the absolute value of a plus b squared is simply equal to this, right? Because we have that, you might know, right? If we have the absolute value of a and b, right? Well, that's just equal to the absolute value of a times the absolute value of b, right? So the product of the absolute values is equal to the absolute value of the product. So that's another useful thing we're going to be using here. And if you expand this out, you sort of get this equality, right? And you can sort of verify that for yourself. But yeah, you sort of get this nice product. And oh, what do we notice, right? We notice that this guy right here is equal to this, right? So these two are equal. And well, we notice that if this squared is just equal to this, well, this is just equal to this, right? But we added on another positive value, right? So if we know that this is equal to this, well, it must be bigger than the other term squared, right? So then we can conclude here, right? Yeah, and again, since the product of the absolute, as I stated, since the product, and yeah, a squared b squared is greater than or equal to 0, right? Oh, sorry. Yep, and right, we have that this term expanded is greater than or equal to this, right? Because, well, what do we know, right? This is just equal to a squared plus b squared. This is a squared plus b squared plus another positive term. So if you add on a positive term to an already positive term, it gets bigger. All right, and well, we know that this holds now, right? Right, so this holds, right? And we already showed, oh, well, this is just equivalent to this, right? So we've just proved, right? This is what we wanted to prove in the first place, right? This is just, right? This is just the modulus of z is less than or equal to real part plus imaginary part, right? So we've proved what we wanted to show, right? Yeah. So absolute value of a means the absolute value, like, yeah. So the bars on a means the absolute value. If it's a complex number, then it's the modulus.
Also, how did you get a squared plus b squared for note that in the first one?
Oh, this
yeah,
one?
Yeah.
Oh, okay. So yeah, good question. So if you take the square root, right? So let's say we have a number and we're taking the square root, right? Well, that's just equal to a1/2, right? And well, if we take the square, right? If we square a1/2, right? That's just a, right? So the idea here is we get back what we have in the square root, right? Because square root and squaring something are sort of like inverses of each other, right? So if I do one, I'm undoing the other. Does that make sense?
Okay, so you're simply computing it and then making a condition and then comparing it with the other one, right?
Yeah, exactly. So I'm just computing this out and then I'm comparing it with this one, yeah, to show that this holds. And we already know, right? This is equivalent to this because we square both sides of a positive inequality. Well, we sort of preserve the inequality, right? Also, this should be greater than or equal to. Also, yeah, I will post the annotated slides, yeah. So yeah, don't worry about that. All right, so we've proved the first half, right? So this is great. We've proved the first half of our theorem, but again, we still have some work to do because we have to show that the second half is true, right? So we only have the first half of our theorem, right? That the modulus of z is less than or equal to the real plus imaginary part. But again, we still have some work to do, right? We have to do this half. All right, so let's get started on this, right? Let's see what we can do. Right, we need to recall our definitions again because you can't prove anything without knowing your definitions, right? So we look, oh, this is just equal to, the modulus is just equal to the square root of a squared plus b squared, right? is this Kaidi's practice midterm? No, this is Kaidi's practice midterm. So if you already feel comfortable with this material, yeah, and also, yeah, this can be called lemma 2. So the last thing we were proving is lemma 1. The other thing we were proving, we can call this lemma 2. Lemma 2, right? So again, we should recall our definitions, because what are we going to prove without knowing our definitions, right? So we already know that the real part of z is a, and the imaginary part of z is b. And we're trying to show that this holds, right? So the modulus of complex number, the modulus of our given z, times square root of 2 is less than or equal to this. So great. Let's continue onwards, right? So first, we're going to make note of another fact, right? So we have this term squared, right? And we know that, well, anything squared is going to be greater than or equal to 0. And you can expand this out, and you'll sort of get something. You'll get this essentially. You can see for yourself, but and we know, right? Well, this is greater than or equal to 0 because it's a squared term, right? So we already know that this is going to be greater than or equal to 0. So we have the inequality that, I'll write this down just so it's explicit. We have this, right? 2ab plus b squared. Great, we have this, right? Why is it minus? Right, so last one we had plus, right? So plus would obviously, we'd get plus 2 absolute value of AB, but it's minus here because, well, we know when we expand this out, we get, well, these, yes. So yeah, everyone, just to make it clear, slides are going to be posted, and I will be posting a recording, so don't worry about that. But yeah, if you notice, when you expand this out, you get a squared, and we know we can just remove the absolute value because a squared is greater than or equal to 0. Then we get a times absolute value of a times absolute value of b, negative absolute value of b, and same thing again. So that would be negative 2 absolute value of ab. No, I'm gonna post it to the Discord, and yeah, it'll be on there. Okay. Yep. Yeah, no worries. Right. So we're gonna make note of the fact that this holds, right? So great. So we have this nice inequality down here, right? Now, you might be looking at this, and does anyone have any idea what should we do here now, right? So just feel free to, oh yeah, don't worry, I'm gonna post these slides, so this will be a complete solution. So yeah. So what does anyone think we should do here? There's something that's sort of, I guess I'll say, popping out, right? All right, so I guess a squared factor. Yeah, so those are all good ideas. Right, so we're gonna add this to both sides. So if you don't recall, this is a absolute value of a plus absolute value of b squared, right? And if you expand that out, you'll get this, right? And we know we're adding a positive value to both sides, or adding any value preserves the inequality, but again, we're adding a positive value, and we notice, right, when we add this value to both sides, right? Oh, we get this, right? We get this inequality. So does that make sense to everyone? So we sort of added this value, right, to both sides in the inequality, and we know, right? We know maybe from A31 or maybe from high school that adding things to inequalities won't change the inequality, right? They'll keep the inequality the same. Okay, so hopefully that's clear. So we get this nice inequality down here, right? Right, and both these values are non-negative. How did we get, okay, yeah. So I should be more explicit with this. So what we did is we took this value, right? And I'm gonna do it right now. We did 0 plus a squared plus 2ab plus b squared, right? So we added this to one side, and right, I did a squared minus 2ab plus b squared plus plus b squared plus a squared, right? Plus 2ab, sorry, I'm running out of room for this, but plus b squared, right? So we got 2 because we're adding b squared to b squared and a squared to a squared. How did you know? Okay, yeah. So they ask a good question. So you don't really know immediately looking at this that you have to add it to both sides, but you know, like you can do that. That is something you can do. And you know, it's sort of a way you can manipulate this into getting what you want, right? So I guess the whole idea of like a proof is that you kind of got to think about, okay, what tools do I have, right? What do I have in my mathematical tool belt? And what do I got to do to get to where I want, right? And you're not going to see this will give you the solution right away. But again, we want some kind of thing that looks like our solution. And we notice here, oh, hey, this guy looks kind of like our solution, right? Because if you factor out 2 from this, well, what do you get, right? You get, oh, look here, a squared plus b squared, right? Which is just the square root of a squared plus b squared squared, right? Is less than or equal to a squared plus, oh no, not a squared plus b squared, sorry. That's wrong. I apologize too, I'm trying to draw with the mouse, so not the most high quality writing, but it should be a plus b squared, right? So this guy looks awfully like our solution. This looks awfully like our solution, right? This guy looks a lot like our solution. So right, and we know these values are non-negative, right? We know that these are, we're all good with these being non-negative, correct? These are both non-negative values. Don't you get the same thing by squaring both sides again? No, yeah, but we're, so keep in mind, we're not assuming that we have this yet, right? We're not assuming that we don't know this yet. We don't know this yet, right? So we're trying to show that this is true. This is what we're trying to show is true. So we don't know this yet. So so when we square both sides, right, we have this, right, and we square this. Well, that's just a plus b. Actually, it should be absolute value of a plus b. I apologize if I caused any confusion. But yeah, this should be absolute value of a plus absolute value of b squared, right? And that's less than or equal to 2 times the square root of a squared plus b squared, right? So this guy looks a lot like our solution now, right? All we need to do is square both sides. And we know we can do that. That's equivalent, right? Because both values are positive. So just to make it clear, in case everyone's a bit confused with that, if I square root a value, right, let's say it's a squared, right, that's going to be equal to absolute value of a. But if a is positive, so if a is greater than or equal to 0, well, this just reduces to a, right? Because absolute value of a positive number is just the positive number. So hopefully that's clear to everybody. So we know that this, so what we had above, let me just go back up. We know that this right here, right? That's equivalent to this because we can sort of go back and forth by squaring both sides and then taking the square root of both sides. Yes, you can only do this if both sides are non-negative. So thank you, Ethan in the chat. Thank you very much. Yes. So you can only do it if both sides are non-negative, right? Right. And oh, what do we know? This is just, that should be, so sorry, I should write this down. It should be the absolute value of the real part times the absolute value of the imaginary part. What's an example of an operation that preserves equality but doesn't preserve an inequality? That's a good question. Let me think. Off the top of my head, yeah, multiplication by negative would do that, right? Because it will preserve equality, but it won't preserve inequality because we have, let's say, a is less than or equal to b. If we multiply by a negative number, there's a chance, like for example, a could be negative and we flip it to a positive value. So that's an example of an operation not preserving an inequality. Okay. So we're going to put our two pieces together. We've proved our two lemmas, and all we need to do now, well, is put them together, right? So before we prove this, right? So this was So this was lemma 1. Oh, this guy, he's lemma 2. Right? And we put them both together, we get a result, right? So there you go. That's the full proof of the first question, right? So we sort of see, right, the sort of techniques we use to do this question, right? We sort of went through and we put the puzzle together step by step, right? So we filled in the outer pieces, the definitions, we sort of, I should write this, right? Should be absolute value. But yeah, we sort of went through, we put the puzzle together very slowly, right? We didn't see the whole solution at first. We worked through carefully, slowly, recalling our definitions and using information we already knew, right? Yeah, so I was gonna ask, does anybody have any questions? So yeah, so great. So Amitaz, great question. So right, I will explain that. Give me 1 second. I'm gonna go to the next slide just so I have somewhere to write on. Right, so our proof is complete. I'm gonna explain how I did that quickly. So right, so we have, okay, 1 second. Is there a specific justification for combining the two lemmas? What do you, so sorry, are you able to elaborate on that a little? Like, we don't really need a specific justification. It just makes the proof much easier to go about, right? Because trying to do this all at once would be a little like a mess, right? We want to break things down because it's easier for us to understand and sort of attack, right? Also, I'll explain how I got root 2. Yeah, so, right, so we'd have 2a squared, right, plus 2b squared. And we can factor 2 out, right? We know we can do that. A squared plus b squared, right? And then then we take the square root. So we're gonna take the square root of this. And what we get is this, right? What we wanted. And we know taking the square root, if both values are non-negative, will preserve our inequality. Can you go over why you squared both sides in lemma 1? Of course, yep, I'll go back. 1 second. Lemma 1. Right. So on lemma 1, right? So what we had was that this holds, right? So we have that this fact holds, right? So that's good, but it's not quite what we wanted to prove, right? This is what we wanted to prove. So the reason we squared both sides is because, well, we wanted to show that this is equivalent to this, right? Which it is, because you square both sides of a non-negative inequality, well, you get back the same, like it preserves the inequality basically. So you can sort of go back and forth. You can sort of think between these two. So we dealt with the case where we had both sides squared because it was easier for us, right? And then we simply squared to go back to show what we proved was equivalent. So does that make sense? Or do you want me to explain again? Is there any particular? Do you want me to explain again? Or do you understand? Okay. All right. Right. Yeah, can I explain? Okay, yeah. So, right. So, okay. Okay. So we know that, so what we proved before we squared both sides is we proved that this holds, right? We have this. So we've proved this, right? Should be something like this. Right, we proved that this holds, but again, we don't have our original inequality yet, right? We wanted to prove that this, the thing inside of the squared is less than this, right? So sorry, this might be confusing. I wrote down the inequality wrong. It should be like this. So we want to square both sides, right? So we can derive what we wanted to originally prove, which was this, right? So we take the square root of both sides and we know that preserves our inequality, right? We get this, which is what we wanted to show. Also, this is equal to C, in case anyone wasn't clear on that before. Isn't it? So yes, but the thing is, it goes both ways, right? So we can either do this and then work towards this, or vice versa, right? Because it's an if and only if. So this is true if and only if, right? If and only if means we can go between them, basically. So if one's true, then the other one's true. If the other one's true, then that one's true, right? So they're both dependent on each other. So proving either of them proves both of them. Does that make sense? Right? So so you might have learned in A67 that you have like a statement like this, like P if and only if Q, right? So this is sort of the same idea, right? So this is an if and only if. So all we need to do is prove one side. Oh, the inequality sign. Doesn't it go both ways? So are you able to maybe, sorry, so isn't it the other way around? The inequality sign. Okay, well, yeah, are you able to elaborate on that just a little more? Sorry, I didn't exactly get the question. I do want to continue on though, because I assume people want to go on to the next question. I want to, shouldn't be this, no, right? Okay, good. Okay, so good question. So no, right? Because what we're trying to prove is, right? So let's go back. What we're trying to prove is this. This is the first part, right? We're not trying to prove that this holds yet. We're at that point, we were just working on the first part. So this should be the inequality we're working on. So obviously, oh, actually, did I write down the signs wrong? Oh yeah, you're right. Yes, they should be flipped, right? Thank you. Yep. Thanks for pointing me out. Thanks for keeping me fully rigorous. Yeah, it should be like that. You are correct. Thank you for correcting me. Sorry, I confused. Sorry, I confused you. Okay. Okay, so this one looks like a big question. So let's sort of break things down and see what exactly we're trying to show here. So we're letting V be the set of all square matrices with real entries. So these are just stuff in the form of, right, probably like 1, 2, 3, 4, 5, 6, 7, 8, 9, stuff like this, right? But it can also be 4x4 matrices, 5x5 matrices. We don't really care what specifically they look like. We just want to know what they're like in the abstract, right? So we're going to let a certain operation, right? So this is an operation defined on it takes in two elements in our space V, and we get an element in the real numbers, right? So it's sort of like, a machine. It takes in two things and it spits out like a number. So we're going to define it as the trace of A transpose B, right? So all the traces it's just the sum of the diagonal entries of a matrix. So for example, maybe have something like this. I'll just write down some random entries. 4, 6, 9. So the trace of this matrix, right? This is equal to 1 plus 0 plus 1, and that's just equal to 2. Right? So do we understand the concept of trace? Just so we're clear, I just want to make sure everyone's good with that. Okay, good, great. Okay, so what we want to show is that our operation, right, if it takes in two of the same matrices, it's going to be greater than or equal to 0. We want to show that the operation on AB is equal to the operation on BA. And we want to show that the operation is linear with respect to a single entry. So we want to show this monster, this gross inequality right here. I know a lot of people are looking at this and going, oh, that looks nasty. But don't worry, it's not. It won't be as hard as it looks. We'll go through it slowly and I'll make sure everyone understands. So, okay. We're going to be using a few theorems, and I just want to make sure everyone's sort of on the same, we're all on the same page about like what's true and what's not. So we're going to be using that. So I guess, so we'll use this fact, right? We'll use that A, B transpose is equal to, right, B transpose, A transpose, right? So hopefully we understand that. We'll be using the fact that A plus B transpose, right? Transpose will distribute across our sums. And I mean, that's pretty obvious, because you take the matrix and you shift it around, right? Well, that's the same as taking the matrices, shifting around the sum after, right? Because you're just summing the 2, 1 shift around. You can sort of just think about it like that. But yeah, we'll be using this. And we will be using that trace A transpose is equal to trace A, right? Because, well, we know if we take the matrix and we sort of shift rows into columns and vice versa, we're not really changing any of the diagonal entries, right? Where the diagonal entries stay fixed. So it's not going to change the trace, because the trace is just the sum of the diagonals. And finally, we're going to be using the fact that trace AB is equal to trace BA, right? Is everyone clear on that? Is everyone clear on why, or did you cover that at all, or do we understand all this? Are we good with all this? Or does anybody have any questions about this? I just want to make sure we're on the same page. Okay, great. Okay, good. So yeah, I just want to make sure we're, I know I'm going a bit slow right now. Why is the last one true? The last one's a little less trivial. I can't really give you a proof right now, but I guess the idea is that you're multiplying the rows. Yeah, it's so, as Ethan said, it's not really a trivial theorem. So I don't really want to go over it right now. So we'll just treat it as a black box. If you don't know it, that's fine. You can just treat it like a black box for now. And you can go back to it later if you're interested in the proof. But we're not going to cover it because that's long and we need to get through the questions. So yeah, let's, hopefully everyone's good. We know the theorems. Well, knowing the proof is a good idea. You don't technically need to know it because you're only going to be using the theorem, but it's a good idea to go over it because it'll give you good math. It'll build your mathematical maturity, being able to go through proofs. So I would recommend going over it. However, we'll treat it like a black box for now, and we'll just get right into the meat, which is the question. So this is a big question. Like we did before, we're going to break it into pieces. Right? So we're going to show that PAA is greater than or equal to 0. So let's recall our definitions again, right? Well, we know that this guy is just equal to trace of A transpose times A, right? Right, and we're going to recall that the diagonal entries of A transpose A are given by the ith row of A transpose and the ith column of A multiplied. I should state multiplied with respect to, oh yeah, sure. Is there something you want to see, or? Okay, great, awesome. Yeah, so we have that the ith diagonal element of A transpose A is given by this. And I mean, you can sort of think of this as like, we have A1, A2, AN, right? This is our, we'll call this our A transpose, right? This will be our A transpose, and we'll say this is the ith row. And we'll have our A right here, and this is our A1, A2, AN, right? That's our ith column, right? So we'll say this is the ith column, right? And we multiply those together, we get our ith diagonal element, right? Because you might remember, for matrix multiplication, to get the diagonal elements, you multiply the ith row by the ith column, right? Okay, so yeah, we have that. That's nice. So everyone's clear on this, right? I know I'm going a bit slow right now. I just want to make sure everyone's like clear with everything. Okay. So we know that's equal to, well, by definition of multiplying a row a row vector by a column vector like that, right? Well, they're equal. So A1 gets multiplied by A1, A2 gets multiplied by A2. So we have all elements squared and we add them to each other. And that's greater than or equal to 0 because when you square a term, it's greater than or equal to 0. So we add them all together, it's greater than or equal to 0. Is that clear? Is that good with everyone? We're good with that? Okay, great. And we're going to recall our definition of trace as the sum of the diagonal entries, right? So we know that trace is just the sum of our diagonal entries. And we know, well, this is an arbitrary diagonal entry and it's greater than or equal to 0, right? Right? So we know that, well, BI is the ith diagonal entry, and that must be greater than or equal to 0 because, well, each diagonal entry, as we've just shown, is greater than or equal to 0. So their sum must be greater than or equal to 0. Right? And well, that's what we wanted to prove. We wanted to prove that this is greater than or equal to 0. So we are done. Done. Right? What is PAA? Good, good. So good question. So that is our operator. So we define this operator above here. So that's our operator, right? This is the operator. And the operator basically takes two matrices and it takes the trace of the first matrix transposed times the second matrix, right? So PAA is simply just trace A transpose times A, right? So does that make sense? Are we good with that? Yeah, okay, cool. And then we're summing over all the diagonal entries. And well, right here, we've shown that they're all greater than or equal to 0. So obviously, if you sum things greater than or equal to 0, it's going to be greater than or equal to 0. So yeah. Okay, so we're going to go on to part 2, right? We want to show that PAB is equal to PBA. And we're going to use an old classic proof technique, right? Start at one side, work to the other, right? So we have this nice guy. We want to work over here, right? To our other nice guy, right? Right here. We want to work over to him, right? He's our nice guy. This is what we want. And we're going to start with him. So we're going to work over to our other nice guy, right? So we're going to recall our definitions. We know that this is just trace A transpose B, right? Right? And well, by definition of trace, transposition is not going to change anything with regards to it because it fixes the diagonal entries. It's just changing the non-diagonal entries. So we can conclude, right, that trace A transpose B, well, that's just equal to trace A transpose B transpose, right? Because transpose preserves trace, right? Great. So transpose also distributes over matrices, but remember, it changes the order, right? So we got to be a little careful here. So we're going to recall that AB transpose is equal to B transpose A transpose, right? So we're good with this? Okay, great. So, right, we have, well, this is just equal to, right, B transpose and then A transpose transpose. And if you, well, transpose the transpose, you're just undoing what you did. So you get back A, right? So in case this isn't, I'll make this more explicit just in case anyone's a bit confused. A transpose transpose, well, that just gives you back A, right? Because you flipped it over and you flipped it back again, right? You can sort of think of it like that, right? Oh, and wait, that's just by definition PBA, right? So we have this guy, and we've shown he's equal to this guy. We accomplished what we wanted to. Yay, right? So we have this guy is equal to this guy, right? By transitivity of equality, right? So this is equal to this is equal to this is equal to this. And finally, we've come full circle, right? We've shown PAB is equal to PBA. Great. So cool. Right, so finally we're going to show the one that's probably the grossest, right? This nasty equality. I'm sure a lot of people are looking at this like, oh no, this is the worst one. So don't worry, we're going to employ our classic proof technique again, right? We're going to start at our guy over here and see how we can work over to this guy, right? He's the one we want to get to. So we're going to use what we know. We're going to use our mathematical tool belt, and we're going to work over to the other side. So again, by definition, right, we'll call a definition of our operator P. that's just the trace of A plus alpha B transposed, right? Times C, right? That's just the definition of our operator, right? Yeah, and again, transpose will distribute regularly over sum. So if I have A plus B transposed, that's just equal to A transpose plus B transposed, right? Right, so we get this, right? So we transpose, and by the way, in regards to transposing a matrix, you can factor scalars out still, so you don't have to worry about the alpha right there. Alpha will just stay outside of it. You can take it out of the matrix and it'll be preserved under the transpose, so no need to worry about that. We don't have to worry about that, so great. And we'll recall matrix multiplication distributes, right? We have the distributive property. Yep, exactly. Yep, thank you, Ethan. Very helpful in the chat. I very much appreciate it, right? So we have this, we get this nice equality, right? So it seems like we got something that's almost working, right? Oh, yeah. And by definition of trace, well, we can split it over sums, right? Because, well, obviously if we have trace A plus B, right? Well, I mean, obviously speaking, we can just take out the parts of A, sum those, and then take out the parts of B, sum those, and then sum it together. So, right, we get the equality trace A plus trace B. Okay, great. So we can do that. So we know that trace A transpose C plus alpha B transpose C, well, that just splits into the sum here. And again, we can factor this out, right? And I want you to sort of think about why we can factor it out, right? But it's pretty, should be pretty easy to see after a little bit. We can factor this out from the trace. This out, right? And then look what we got, right? This is just by definition, right? We see this is just by definition our operator on AC, and then alpha times our operator on BC. And what do you know? That's what we want to show, right? We want to show equality between this and this, right? So we've proved what we wanted, so that's great. So we proved this. Fantastic, great. So we finished our proof, right? So we want to show that, and that concludes part one of this question, right? That's what we want to show. We throw out all three things, and I'm not going to go too much into this. I don't want to scare you anything. It's not necessary for this class, but we almost just proved that our operator is an inner product, right? So this is sort of a special generalization of the dot product. You'll learn more about this in MATA22. I don't think dot products also came up either, but yeah, the dot product is a nice product in linear algebra. You'll probably learn about it later on. And this is sort of a generalization of that. So P is a sort of more general dot product on matrices, but whatever. Dot product not relevant for the midterm, I believe. I don't know what's relevant to your midterm, but unless he explicitly stated is going to be on there, don't worry about this. But you will be seeing it in B24. So for part two of this question, we want to show that if D is symmetric and S is skew symmetric, then PDS is equal to 0. Okay, so this seems kind of difficult at first, right? We have two abstract matrices, like there's two arbitrary matrices. We're trying to show their product is equal to 0. However, something we know, so we know that A equals negative A implies that A equals 0 for all A in the real numbers, right? Hopefully we're clear on this, right? And we know our operator outputs to the real numbers. So we know if we can just show PDS is equal to negative PDS, then we can get that it's equal to 0, right? We do need to know dot product. Okay, yeah, so yeah, you need to know dot product, but don't worry about inner products. Okay, but yeah, this is hopefully this is clear to everyone because like no other real number is going to satisfy this equality other than 0. So that's what we want to show. So we're going to want to show PDS equals negative PDS, right? And that's how we're going to show it's equal to 0.
Can you explain the above one again?
That this is an A. Can I explain the above one?
Yeah, this one. We know that. No, same question.
Right.
Yeah. So, yeah.
We know that, so A is equal to negative A. That implies that A is equal to 0, right? Well, because if you have a real number and it's equal to the negative of itself, well, clearly the only possibility is that that number is 0. So what we're going to do in this proof is we're going to try to show this. So we haven't actually done the proof yet, but I'm just going over the technique we're going to be using. So does that make sense?
Yeah, it does.
Okay, awesome, great, thanks for asking questions. Always good. Everyone learns from that. So let's start, right? I don't want to take up your time, so let's recall our definitions, right? This means that, right? So D is symmetric, so we know that D transpose is equal to D, right? And skew symmetric just means the transpose is equal to the negative of that matrix. Right, yeah. So we're showing that because, right, we want to show that it's equal to 0, right? And we know that if that equality is true, well, then it has to be equal to 0. There's no other possibility. So that's why we're trying to show that, right? Because the only real number that satisfies that property is 0. So is that clear? Yeah, no worries. So this means that, right, D transpose is equal to D and S transpose is equal to negative S, right? And that sort of comes from the fact that D is symmetric. So symmetric means that it's equal to its transpose. And S is skew symmetric, which means its transpose just the negative of it, right? So you multiply by -1. Okay, great. So again, as I stated, we're going to employ the approach here. We're going to show PDS equal to negative PDS, right? Hopefully that's clear. Right, so recalling what P is again, we have PDS, right? That's the trace of D transpose times S. That's the definition of our operator, right? Oh, okay. Right, so D is symmetric. So by definition, D transpose equals D. And we're going to use the fact that transpose preserves trace, right? Because it fixes the diagonal entries, right? So we get this equality, right? So we get trace D transpose S. Well, we know that trace preserves the D is symmetric, so it's preserved under transpose. We have just trace DS, right? And we can take the transpose and that will preserve the trace. And again, we have, right, trace distributes over here, but we switch the order. So great, we have this nice equality, right? And by definition of skew symmetry, S transpose is equal to negative S. Oh yeah, of course. This page, or is this good? Okay, well, yeah, so is that good? Or do you want me to answer any questions about it? Okay, I'm gonna continue on because I know people want to actually get on with the question. So by definition of skew symmetry, right, we have S transpose is equal to negative S. So we get, well, trace S transpose D transpose is equal to trace negative S dt, right? And recall, we can factor out scalars from the trace, right? Because scalars aren't going to affect the sum because we can just multiply the sum after by the scalars, right? Why do we transpose dn again after, why do we transpose ds after trace? Oh, you mean this part, right? Yeah, so we're trying to work towards the equality, right? That our operator PDS is equal to negative PDS, right? So we're trying to sort of, I guess, extract the negative from S, right? We're trying to extract the fact that S transpose, right, equals negative S, right? We're sort of trying to extract that fact. So we have to take the transpose, right? And we know that trace is preserved under transpose. So that's sort of the fact that allows us to sort of do that, right? So what we're trying to do here is sort of extract the given information, right? We're given that S is skew symmetric and we want to use that fact, but we need to get ourselves in a position where we can. So that's sort of the idea, right? We're transposing because we want to get to S transpose, right? And that's sort of the only way we can do that. Does that make sense? Okay, awesome, great. Right, so now we're going to use the fact that trace, right, trace AB is equal to trace BA. How did we go from trace DS to trace DS transpose? Right, yeah, so transpose preserves the trace. So if I take the transpose of any matrix inside the trace is going to be the same. So we have equality because you can sort of think of it as like, if we take the trace, or if we take the transpose of the matrix, we're fixing the diagonal entries. So the diagonal entries, they stay the same. So the trace isn't going to change because the trace is just the sum of the diagonal entries. Is that clear? Okay. Yeah, I do want to get on because I know we gotta get through all the questions. So yeah, I'll answer questions after, right? So we have this equality, right? Because trace matrices commute in the trace. We can take trace S D transpose, and that's equal to trace D transpose S. Oh, and what do we know? That's just PDS, right? We should do P comma DS, right? And that's exactly the equality we want to show, right? PDS is equal to negative PDS, right? We know that this is equal to PDS, right? PDS, right? We sort of worked all the way from here down to here, right? So we've worked towards what we wanted, right? We have this nice equality. And well, the only possibility is that it has to equal 0 because the only real number that satisfies the property that it's equal to its own negative is 0. So it must be 0, right? Does that make sense? With respect to. When I say with respect, when I say WRT, it's with respect to. So I just mean like you can take trace of AB and that's equal to trace BA. Yep. Awesome. Okay. So let A be a square matrix with real entries, and it's going to be symmetric. So we'll just write this down. A transpose equals A, right? It has this neat property, right? So X transpose A. So if we have like a vector X, so let me just write this out. X1, X2, right? Xn, right? Transpose. Well, this is just equal to the row vector, right? So X1, X2, Xn. Great. So we have this, right? We have this nice, just if you're not aware of what that was, right? Right? And it's greater than 0 for all X in Rn, right? X not equal to 0, right? We're going to let B be a skew symmetric matrix. So we know that B transpose is equal to negative B, right? We're going to let that be a skew symmetric matrix. And we want to show that the sum, right, that A plus BX equals B for all B in Rn, that has a unique solution. So we can find a unique X such that A plus BX equals B, like for all B in Rn. So there's no, like, we can find one that's going to be the only solution, right? Is that clear to everyone? Right, okay. Not really. Okay. How do we know that X is a vector? Right, okay, yeah, so, right, when I made these slides, I actually didn't know how to add the little arrows on LaTeX, but yeah, normally there would be an arrow over here, but we know that X is a member of Rn. Yeah, so it has X with an arrow on the top, but I mean, we've specified that X is a member of Rn, right? So the arrow is good for like notation wise, but you don't really need it to know it's a vector. We already know it's a vector because we defined it to be one, right? So just imagine X being a vector in Rn, right? You can write any symbol for a vector. You should put the arrows, like it's good notation, but I didn't know how to add the arrows in LaTeX. So yeah, I apologize. Thank you, by the way, thank you, Ethan, for giving me the LaTeX notation. But yeah, you can just think of X as like a vector, right? So just ignore the fact there's no arrow. But yeah, it's a vector, right? So let's recall what it means for an equation to have a unique solution. So I don't know, did you all cover linear independence yet? Okay, good. So if all the columns of A plus B are linearly independent, then we know like this has a unique solution, right? Is that because it's a square matrix? So if all the columns are linearly independent, then we know that it must be bijective, right? That clear? Right, yeah, of course. So if I have like three vectors, right? X1, X2, X3, right? Maybe I have Y1, Y2, Y3, right? And then I have Z1, Z2, Z3, right? So we say that two vectors are linearly independent, right, in a set if there is no way to write them as a linear combination of any other vectors in the set. So you can't like write them as a linear combination of any other two vectors in that set, right? So right, they're unique. Like they basically add to the set, right? They add possible vectors you can span with, right? Is that sort of clear? No parameters. Yeah, so hopefully, sorry, I didn't explain that very well, but that's the gist of it, right? That's the idea. We have three vectors and they can't be written as a linear combination of each other. That's linearly independent, and well, the converse of that is just linearly dependent. Okay, so we'll also recall, I hope, so is everyone familiar with this? So this is true if and only if a plus b x equals 0 implies x equals 0. So the only solution to a plus b x equals 0 is x equals 0. So is this clear to everyone? Did you cover this? I just want to make sure I'm not using stuff you didn't go over yet. But yeah, so this is if and only if. So we're going to use this theorem here, right? So we're going to start off with, right, we take a vector x in our space, and we're going to start off with a plus b x equals 0. And we want to show, x equals 0, right? Yeah. So yeah, okay. So good, Patty covered that. That's great. Okay. So we want to work towards x equals 0, right? So we're going to do that. Why a plus b cannot equal 0? No, I don't think it's a plus b cannot equal 0. I think we're trying to show that if a plus b x equals 0, then x equals 0 is the only solution to that. Okay, so yeah, I don't want to spend too much time. Right, so we're going to show x equals 0 from that, right? Right, so by distributivity of matrix multiplication, so we recall matrix distribute with respect to matrix multiplication, we have this equality, right? So we have ax plus bx equals 0, right? And well, we can carry over bx, right? So we can carry over bx to the other side. So we subtract, so I'll just make it explicit. We subtract bx from both sides and we get, right? Oh, ax equals negative bx. Great, so that's awesome. So that's a start, right? So we're going to take a little bit of a detour and consider x transpose bx, right? Because we're going to recall, I'm going to go back up. That was part of our given information, right? Oh, sorry, no, never mind. No, yeah. So we're gonna take a little detour, right? We're gonna consider this value, right? So we want to show this is equal to 0. And can anyone sort of figure out why we want to show this is equal to 0? Like, can anyone think of why we wanted to do that given this equality? So I guess you can sort of just think about that for now, but we're gonna go on because I don't want to take up too much time. So we're gonna note that x transpose bx transpose, well, that's just equal to x transpose. Yeah, because, yeah, so x is, b is the symmetric one, correctly. Right, so, yeah, so that's a skew symmetric. So I actually think that should be negative. Yeah, maybe I messed up on these slides. So, okay, we have x transpose bx is equal to x transpose bx, right? Does that make sense to everyone? So it's sort of equal to, should be negative. I think there should be a negative there. Yeah, exactly. We want to show that ax plus bx equals 0, right? Yeah. So, right, that should be a negative there, I'm pretty sure, right? Oh, no, it's also, no, okay, no negative, right? We know that, well, this, right? So we have bx, right? And this is a vector. So this is a vector, right? So this is a column vector. And then we have x transpose here. And that's a row vector, right? Vector. And when we multiply these together, well, we get a value alpha, right, in R. So we get a value that's in the real numbers, right? So if you take the transpose of a value that's in the real numbers, well, what you get is just, it's equal to its own transpose because it's just one thing. So there's nothing really to swap or anything. So it's equal to itself, right? So is everyone clear on why that holds, right? Is everyone clear about why this thing's transpose is equal to itself?
Not quite.
Okay, yeah, I can sort of like do it right now. So, right, so I'll just write it down right now. So if I have x, right, you have x1, x2, xn, right? And I multiply this by b, and I'll maybe have this, right? So x1, xn, right? So this is just equal to, so I'll just write it out right now. So this is just equal to this product, right? So that's just equal to that, right? And when we multiply a matrix by a vector, right, we get another vector. So we get something like x1, xn, right? And this is probably, we'll call this b1 through bn, right? And we know, well, the definition of this multiplication, we simply get x1, b1 plus xn, bn, right? And that's just the sum of real numbers. And a sum of real numbers is in the real numbers, right? And if you take the transpose of a real number, right, that's just, you get the same thing back, right? So does that make sense? Hopefully that's clear. Does that make sense to everybody?
Why is b times the column vector just a column vector?
Well, okay, yeah, so good question. So that sort of follows from the definition of matrix vector multiplication. So I have a matrix, right? Let's say A, right? And it's like, I don't know, we'll just put A, B, C, E, F, G, H, I, J, and we multiply that by, I don't know, we'll say alpha, beta, and phi, right? And this is just our vector, right? So we'll call this V, right? This is equal to, right? A plus B plus C, right? Alpha plus EFG beta, right? Beta. And then H, I, J, phi, right? And well, that's just the sum of vectors, right? And the sum of vectors is just a vector, right? So is that clear as to why that's a column vector?
Yeah.
Okay, great, awesome. So we have by distributive transpose, there should be a right there. Yeah, so by distributive of transpose, right? Because transpose distributes over the matrices, but swaps the order. So just keep in mind it swaps the order, right? We have this equality, right? So x transpose bx transpose, right? Well, it's this, right? It distributes over each of the components here because these are all technically matrices, right? Yeah. And then, well, oh yeah. So sorry, this is actually sort of a mistake. We're not subtracting, so I'll just erase that. This is just negative, and then we're multiplying these two together. So sorry about that. Right, and that's just negative x transpose bx, right? Hopefully that's clear, right? Right, so we have x transpose bx transpose, we have it equal to this, right? But we've also shown, right, that this is also equal to this, right? So by transitivity of equality, right, we get this equality, right? So x transpose bx is equal to negative x transpose bx, right? That's really good, right? And it's a real value quantity. We know it's a 1-by-1 matrix, which is just a real number, right? So we have it must be equal to 0, right? Are we doing the transpose to x transpose in the first step? Yes, we are. We're doing transpose to everything, right? But you notice like we would swap the x in the third component, it would go to the first one. So this would be transposed, right? So that would go here. Then the b is transposed, it stays in the middle, right? And then we have the last x is transposed, right? But transpose of a transpose, that just undoes it and it gets sent to the front, right? Hopefully, yeah, hopefully. Wait, but we didn't ignore the negative sign on the last page. We're not ignoring the negative sign anywhere. We're just trying to show that like, right, we were just trying to show that this is equal to this, right? So we're not ignoring the negative sign.
Wait, can you go over again why that first transpose is equal to the negative of it, like that top line?
Right, yeah, of course. So we know, right, we know this transpose, right? If I take 3 matrices, right, A, B, and C, and I transpose them, well, inductively, we just apply our same principle, right? So B goes to the C transpose goes to the front, B transpose stays fixed, and A transpose goes to the front, right? So we do the same thing. So X transpose goes to the back, B transpose stays in the middle, and then like X transpose goes to the front, right? And transposing a transpose, that just gives back the original vector, right? And we know that B is skew symmetric. So B transpose, that should be B transpose, I apologize. B transpose is just equal to negative B, right? So I should put brackets on there, right? So B transpose is equal to negative B, right?
Oh, those brackets were what were
yeah, I
apologize.
I apologize. I'm really sorry. When I was making these, I didn't check some of them over. So thank you. Thanks for pointing that out in case anybody was confused. Yeah. So it should be B transpose. And then this is bracketed. So we have negative BX, right? And we can factor the scalar out. Right? Right. So we're going to go back to our original inequality. Right? AX is equal to negative BX, right? And we can multiply both sides by X transpose, right? And why can we do this, right? Let's think about it. Well, we obviously this is defined. We know it's defined because this is a vector, this is a column vector, this is a row vector of the same size, and likewise for negative BX, right? And we get X transpose AX is equal to negative X transpose BX, right? And that's equal to 0, as we've just shown. Yep. And we're given that for all x in R, so that should be the real numbers, right? Sorry. X is not equal to 0. For x not equal to 0, X transpose AX must be greater, strictly greater than 0. So the only possibility here is that X must be 0, right? There's no other possibility. Like, we cannot have any other possibility here because, well, obviously, X transpose AX wouldn't equal to 0, right? It would be greater than 0, right? So the only possibility here is that X has to be specifically 0, right? We know that, right? And that's what we want to show, right? We started from here, right? And we wanted to show that X is equal to 0. And well, we did that, right? So we've shown that A plus B X equals 0 implies X equals 0. So we know that A plus B must be a square matrix with linearly independent columns. So it must be invertible. So that's it. We've proved what we wanted to show. That's great. Awesome. So that's wonderful. Great. So we're going to do question 4A, right? We're going to go on to our next question.
Can you go back really quick?
Oh, of course. Yeah. Is that good?
I'm still confused on the last statement where you say X is not equal to 0, but then you say X must be 0.
Yeah. So the property of, so we're given a property, right, of our matrix that for all X in the real numbers, for X not equal to 0, X transpose AX is greater than 0. So that's just a property we're given, right?
Oh, okay.
Yeah, but we know that, oh, this is equal to 0. So what must be true of X? Well, X must be 0 because
I thought that it was just a constraint for all X. I didn't know.
Yeah, no worries. Yep. Thanks for asking. Yeah.
Thanks.
No problem. Okay, so we're going to go on to question 4a. So we're going to let A and B be square matrices, and we're going to assume they share some common eigenvector, right? And we want to show that the determinant of AB minus BA is equal to 0. So I don't know if you went over this yet, but we're going to recall we're going to be using a theorem. So theorem. So product of eigenvalues of A is the same as determinant of A. So they're the same thing. If you take the product of all the eigenvalues of A, you get the determinant. Did you cover this or no? I just want to make sure we're all on the same page. Oh, okay, great. Heidi showed it. Awesome. So yeah, so this is a thing. So this is a thing. So in case you didn't know that, I just wanted to set the groundwork so we know, right, what theorems we need to use. So if you don't know the proof to this, don't worry about it. We'll just treat it like a black box for now. We'll just use it as a tool. And if you're interested in the proof, it's probably in your textbook. We don't need to get rid of that. I can just go on to the next slide. Okay, so we know that A and B share an eigenvector. So let's call this the vector V. And we'll say that AV is equal to lambda 1V. So lambda 1 is the eigenvalue of V with respect to A. And lambda 2 is the eigenvalue of B, or the eigenvalue of V with respect to B, right? Yeah. So, and also you don't need to memorize proofs. Don't memorize proofs. That's not the point. The point is to sort of go through the proof and realize the common tools you're using, right? So you do want to memorize the techniques you use. Like you do want to remember those. You don't want to memorize the specific proofs though. The techniques and the ideas are what's really going to help you, right? So this should be a pretty straightforward proof then. We're going to consider AB minus BAV, right? And well, by distributive matrix multiplication, he's a very helpful property, right? We get AB minus BAV. Well, that distributes, right? Oh, and what do we know? V is an eigenvalue of B, and it's also an eigenvalue of A, right? And it has corresponding eigenvalues, lambda 1 and lambda 2. So we get ABV minus BAV is equal to A lambda 2V minus B lambda 1V, right? Right, is that clear to everybody? We're good with that? Okay, let me go on. Right, and we're gonna apply the same reasoning we did before, right? And we're gonna first factor the scalars out, and we know we can factor scalars out from matrix multiplication. They commute with respect to all the matrices and vectors. We don't need to worry too much about those. Yep, can I go up? Of course. Yep, okay. Awesome. Okay, great. Okay, so, right.
Previous slide, if that's okay.
Excuse me?
I have a question on the previous slide.
Yep.
Could you explain the last statement?
Right, yeah. So we have the matrix AB times V, and we're obviously minusing that. And we know, right, that V is an eigenvalue of B, right? So we know we'd take the product of V with B first, and we know that's equal to lambda 2V, right? And then we're still multiplying that by A because we haven't multiplied by A yet, right? So we still need to do that. And it's the same sort of logic for the second half.
Got it. Thank you.
No problem. Right. So we know that, well, AV, that's simply equal to lambda 1V, right? Because that's its eigenvalue with respect to A. And likewise, same thing for B. Oh, but what do we know, right? We have lambda 2 times lambda 1V, and we're subtracting that from lambda 1, lambda 2V. Well, real numbers commute, right? We know that. We're familiar with that property, right? We're subtracting the same vector from itself, so that's equal to the 0 vector, right? So maybe I'll put over, just so we're clear, this is the 0 vector, right? So that's a vector, right? So we have that AB minus BAV is equal to 0 times V, or the 0 vector, right? So it sends V to 0. So 0 is an eigenvalue of AB minus BA. And recall the theorem that we're going to recall the theorem. We're going to use this theorem now that the determinant is the product of, so the determinant of AB minus BA is the product of its k eigenvalues. So we're going to assume it has k eigenvalues lambda I, right? And 0 is one of them. We know 0 is one of them, right? So there's going to be some notation you might not know coming up. So I'll just explain it in case anyone doesn't know, but it's pretty simple. Right, so we know that product of anything with 0 gives a 0, right? If you multiply anything by 0, we get 0. And one of our lambda i's equals 0, right? So we have, right? We have det AB minus BA. And if we don't know what this is, so I'll just explain this quickly. This is just, right? You probably know about sigma now, but for products. So yeah, it's just sigma, but for multiplying. So yeah, that's the idea. It's not too complicated, right? Right, and we know, well, we have a 0 in here, so the entire product must be 0, right? And that's what we wanted, right? That's what we wanted to show, that the determinant is equal to 0. And we know that if the determinant is equal to 0, well then, right? If the determinant is equal to 0, sorry, let me look back. Oh yeah, no, that's what we want to show in the first place. Yeah, I thought we were. Yeah, so that's what we wanted. We wanted the determinant is equal to 0, right? But yeah, so is everyone clear on that proof? I thought it was pretty simple, but in case, like if anyone doesn't understand, feel free to ask any questions. Like I don't want anyone being confused. Is this theorem in the textbook? I actually don't know. I haven't read your textbook, so I don't know. But I heard Kaidi covered it, so in the review seminar. So I assume it'd be fair game.
Sorry, can you explain the first line on this slide again?
Right. Yeah. So, right, we have this. We have this. We're starting off with this. So we agree with this, right?
Yeah.
Okay, so we can take the scalars out, right? We know we can take the scalars and bring them to the very end, right? Because those commute, right?
Right.
So we get this, right? And we're just doing the same thing we did again last time, right? We know V is an eigenvalue of A, so AV is equal to lambda 1V, right? And same idea, right?
Oh, okay. Yeah, I see.
Awesome.
All right, thank you.
Great, no problem. Okay. This one is a bit more yucky, but we'll try to make it as understandable as possible. So we're going to let A be a square matrix, and we're going to prove that for sufficiently small choice of epsilon greater than 0, the matrix A minus epsilon I is invertible. Okay, let's get started. So obviously this seems like a pretty awkward problem, right? It's might be a little difficult to see how you'd approach this, but let's sort of feel things out, right? Right. So let's, we know that lambda is an eigenvalue of A. So we're gonna consider a lambda to be an eigenvalue of A with corresponding vector. That should be vector. Sorry. Vector B. Right. And at least one must exist. And this follows from the fact, I don't know if you all covered it yet, but this follows from the fundamental theorem of algebra, right? That every polynomial of degree n has n solutions in the complex plane. Okay, but yeah, we know at least one exists, right? So we're then going to note down that, so we're going to note that A minus epsilon IV, right? Well, we know that matrix multiplication distributes, right? So we get AV minus epsilon V, right? And by distribute, we know that follows from distributive property, right? We then note, right, that AV minus epsilon V, well, V is an eigenvalue of A, so we know it's sent to lambda V, right? And then we subtract epsilon V still. And then these are both scalars, so we can just factor them out like this. So we know that if we have some eigenvalue lambda of A, right, with eigenvector V, then A minus epsilon I will have lambda minus epsilon with an eigenvector v, right? So we know that if lambda is an eigenvector of A, then lambda minus epsilon must be an eigenvalue of A minus epsilon I. Is that clear to everybody? Yeah. Oh yeah. Can I scroll up? Of course. Great. Can I explain that again? Yeah. So we have A minus epsilon IV is equal to AV minus epsilon V, right? That distributes over. And we then note, right, that, well, V is an eigenvalue of A, right? So that gets sent to lambda V. Why did you multiply by V? No, we're not multiplying by V, where V is a vector, right? We're multiplying A, or yeah, well, we're not multiplying anything by V, right? V is just an eigenvalue of A, right? So we're doing A times V, right? There should be brackets. Oh yeah, he's right. So, right, yeah. So yeah, there should be brackets here. What we're doing is we're multiplying by this, right? So it's like this. It's that product, right? And why is there one eigenvalue again? Yeah, so we know there's at least one eigenvalue, and that follows from the fundamental theorem of algebra, right? So you compute the eigenvalues by finding a polynomial, right? That's your characteristic polynomial. And we know that has at least one solution, right? Because it's at least going to be degree 1, right? And by the fundamental theorem of algebra, every polynomial of degree n has n solutions in the complex plane. Zero eigenvalue twice from lambda. Right, yeah. No, sorry. I should have fixed that. It's eigenvector. Eigenvector phi. So I apologize. Yes, that should be eigenvector. But is that clear to everyone? Is everyone clear? So does an eigenvalue, at least one eigenvalue will always exist for a matrix. And that follows from the fundamental theorem of algebra. Did you cover that or no? Did Kaidi cover that? I don't remember if he did or not. If he didn't, don't think so? Okay. Yeah, but you do know that every matrix is going to have at least one eigenvalue. So you can be sure of that. Okay. So, great.
Okay, I have a quick question.
Yeah, of course.
Yeah. So so if a matrix has an eigenvalue, so it also has to have an eigenvector.
Yes. So that sort of follows from the definition of an eigenvalue, right? So an eigenvalue is just some scalar multiple A will send some vectors to. So AV is equal to lambda V, right? So there has to be by definition a vector that V sends to lambda V for it to be an eigenvalue. Foya lambda.
Right.
Okay, great. Okay. So we have by definition of an eigenvalue that A has an eigenvalue of lambda with eigenvector V, then we know that our other matrix, A minus epsilon I, will have an eigenvalue lambda minus epsilon with the same eigenvector, right? But we're not done yet, right? Because what if A minus epsilon I has eigenvectors that aren't in this form? So all we've shown is that if A has this eigenvalue, right, then A minus epsilon I has this eigenvalue. But that's just an if-then condition. We need to prove the converse because we want to show that the eigenvalues of A minus epsilon I, right, are simply the eigenvalues of A shifted over by epsilon, right? So we need to show that this is an if and only if, right? So we want to prove this. If lambda, that should be, sorry, I should have fixed that. This should be epsilon. I don't know why I made these really late at night, so I might have made a lot of mistakes in them. But yeah, this should be, if lambda minus epsilon is an eigenvalue of A minus epsilon, that should be I. I don't know if I make so much mistakes in these slides. So if lambda minus epsilon is an eigenvalue of A minus epsilon I, then lambda is an eigenvalue of A, right? We're trying to show this is an if and only if relation. So we want to sort of back and forth, right? So that's good. Now this seems really hard to prove directly, but let's recall, right? One of our trusty proof techniques, right? Contrapositive. So let's recall what this means. So recall if we had something like P implies Q, well, this is equivalent to not Q implies not P, right? So we're going to use contrapositive for this because it might be easier to sort of see this with contrapositive. So what we're going to prove, right, is that if lambda is not an eigenvalue of A, then lambda minus epsilon is not an eigenvalue. This should be epsilon again, of A minus epsilon. And again, should be I. I'm sorry, this should be I. Just pretend it's there. Right, so we're gonna prove that instead. But is it clear as to why those two statements are equivalent, or do you want to just explain again? Are we all good with contrapositive? Are we all comfortable with that? Okay, good. All right. Right. So we're going to assume that for all vectors v, right, lambda is not an eigenvalue of A, right? So then we're going to assume that AV is not equal to lambda v. Then we're going to investigate A minus I epsilon, right? So the best thing to do with these kinds of things is sort of feel it out first and see, right? Let's see what happens, right? Let's see what properties our objects have, right? So we're going to look, right? We're going to see that A minus I epsilon v, right, by just distributive property of matrix vector multiplication. Oh, yeah. Yeah, so I'm just going to go back, sorry, back to the missed final statement. Okay, yep, no worries. All right, so I'm going to go on now, right? So we know by distributive property of matrix multiplication, this holds, right? Right? And well, we know, right? This cannot equal, why do I keep forgetting to like actually make it an epsilon? Sorry about that, everyone. But we know that this is not equal to this, right? Because AV is not equal to lambda V, right? But these are equal to each other. So the only thing, so we know for sure this cannot be an equality, right? And we know we can factor these both out, so we get lambda minus epsilon V, right? So we've shown, right? AV minus epsilon V cannot equal this. So we have not equal, right? So what we've just shown is that if lambda is not an eigenvalue of A, then lambda minus epsilon is not an eigenvalue of A minus I epsilon, right? So by contrapositive, we have that lambda is an eigenvector of, or not an eigenvector, an eigenvalue of A if and only if lambda minus epsilon is an eigenvalue of A minus epsilon I. So is that clear to everybody? I know that's a lot. I know there's a lot to take in. This is a pretty gross proof. So if anyone's not clear, you can feel free to ask questions or anything.
Okay, just to be clear, so you're saying that AV minus epsilon V is equal to lambda minus epsilon V if AV is equal to lambda V, right?
Exactly. Well, if and only if. So those are equivalent.
Only if. So if AV is not equal to lambda V, so then it cannot, so AV minus epsilon V cannot be equal to lambda minus epsilon V.
Exactly. That's the idea. So we sort of proved the contrapositive, right? So what we wanted to prove here is that if lambda minus EV is an if lambda minus epsilon is an eigenvalue of A minus epsilon I, then it's an eigenvalue of, then lambda is an eigenvalue of A, right? So we're using the contrapositive to show that it's, right, the converse, or not the converse, but the contrapositive is true, right? And we've proved that it's an if and only if relation. So lambda is an eigenvalue of A implies lambda minus epsilon is an eigenvalue of A minus I epsilon. Is that clear?
Yep.
Awesome, great. Okay. Why is the last
question?
step?
Isn't there supposed to be a lambda minus epsilon at the last line? Is there supposed to be a brackets around them or no?
Yeah, there should be a bracket. Thank you for letting me know. There should be brackets around them. Technically they're two scalars, so you could ignore them, I guess. But like, yeah, you're right. There should be brackets around them. So thank you for pointing that out. Right. So again, we got lambda minus E is not an eigenvalue of A minus I epsilon if lambda is not an eigenvalue of A. So this is just as we wanted, right? So that's great. So we have by contrapositive, right, that lambda is an eigenvalue of A if and only if lambda minus epsilon is an eigenvalue of A minus I epsilon, right? So it's an if and only relation. So we kind of have a back and forth, right? These two things are actually one and the same. They're equivalent, right? Right, so we know that if A has all non-positive eigenvalues, right? So then for all lambda, that should be negative, sorry, this should be negative. So we know if all the eigenvalues are negative, right? Then for all lambda I of A, right, we have, so let's assume that all lambda I minus epsilon are less than 0, right? Then we know from our theorem that the determinant is the product of the eigenvalues, right? We know that this isn't going to be equal to 0 because, well, we know, right? If we take the product of a bunch of things that aren't 0, then we aren't going to get 0, right? The only time we get 0 is if we multiply by 0. Now, I know you're probably thinking, well, that's great, but we don't know that all the eigenvalues are negative, right? So we got to look at the other cases. So let's investigate those cases, right? Well, okay, if A does have, it should be, right? Right, so if A does have m positive eigenvalues, right, then we can just choose the minimum of those positive eigenvalues, right? And this exists because it's a finite set, right? So the minimum of a finite set of ordered numbers, or a finite set of numbers, right? The minimum is always going to exist, right? So we can just choose sufficiently small epsilon, because we can choose epsilon. It can be arbitrarily, we can make it as small as we want, right? We can choose epsilon such that this inequality holds, right? For all the positive eigenvalues, right? If we had negative eigenvalues, then they would just be, let's say these are our negative eigenvalues, they would just be like this, right? But the point is, we still get within this inequality, right? So we can still land within this inequality, right? Oh, and we still get, right, that our determinant cannot equal 0 because either the values are greater than 0 or they're less than 0 for some epsilon. So is that clear to everyone? Again, I know that was a lot. So if you have any questions about that, please let me know. Or is that clear to everybody?
Yeah, if you can just explain the part again, the middle part again.
Oh,
What is-
this one?
Yeah.
Yeah, so we know that, right, so we know that A has some, if A has positive eigenvalues, then it must have some minimum positive eigenvalue, right? And we know we can just make epsilon small enough, right, so that epsilon minus that minimum value is still greater than 0, right? Because for any real number greater than 0, right, you can always pick some epsilon that will be small enough such that epsilon minus that number will still be greater than 0, right? And we know that for all the other positive lambda i's, right, that, well, them minus epsilon, because those lambda i's are bigger or equal to our minimum, right, those are still going to be greater than 0 too, right? Is that clear? Sorry, I know, again, I know that's a lot. It's, yeah, it might be a little difficult to explain clearly in one go. So is that clear?
Yeah, it is. Thank you.
Yeah, I just note these lambdas from I equals 1 to m, these are our positive ones. If we have negative ones, then we just apply the same reasoning. If we have a mix of positive and negative, then we just apply a mix of these reasonings, but it's the same argument, right? Okay, great.
Is it A minus identity time epsilon?
Excuse me?
Is it a matrix A minus identity matrix time epsilon?
Yep, that's
okay,
correct.
okay.
Yep, so since our determinant is non-zero, our matrix is invertible, and that's what we wanted, right? We wanted to show that the determinant was non-zero, and we got that, right? So yay, we've solved the proof. Let's go. Okay, so question 5, this one's kind of a doozy, so let's strap in because this is another pretty long one. So we're going to define function t from Rn to Rn, and we're going to define it like this, right? So we have tx1, x2, xn, right? And it's x2, so the second component minus the first component, third component minus the second component, all the way up to xn, where we take x1 minus xn, right? So we seek to answer two things. Is T invertible, and what are its eigenvalues? So the invertible case is pretty easy. We just fish for a counterexample, right? And we know I found a counterexample, right? So we're going to recall that it's invertible if and only if TV equals B has a unique solution for all B, right? So, I mean, it's pretty intuitive, right? To be invertible means, oh, if I send something to our range, to our codomain or our range, right? Well, then I should be able to go pick that thing and say, oh, okay, that came from this, right, in our domain. So it needs to have a unique solution, right, for all B. So we're going to choose some B such that TV equals B has two solutions, right? So we're going to consider B is equal to -1, 0, and then all the way to 1, right? And we see that, right, for T1, 0, 0, 0, oh, that should be bracketed. I'm sorry, everyone. Should be brackets around there, right? We see that this is the case, right? Because we have 0 minus 1, 0 minus 0, and then we have 1 minus 0, right? And that gives us -1, 0, all the way up to 1. So with this choice of V, we get B. But also, we have a second V, right? We have a second V, right? So we have, this is our second V, right? And we have B, right? And once again, right, we get B, but our V is not the same as our first V. So we don't have a unique solution for this given B, right? Why is x1 only 1? Let me go back. Okay, why is x1 only 1? Are you able to? Yeah. You can do this for multiple B. Like, it doesn't have to be. You can choose whatever B you want. Honestly, you just need to show that there exists a counterexample. I don't really understand the question. Why is x1 only 1? Actually, no, yeah. Okay, so yeah, so we, yeah. Are you asking why we chose this? We just sort of chose this because it's a counterexample, right? Does that make sense? Yeah, it could be anything. We can choose any V's we want and any B's we want. There just has to be. Yeah, I mean, this is how we do it, right? We're using a counterexample. So how you would check if it isn't invertible, you would either give a counterexample, or you could find a matrix for it too. I don't know if you covered that yet, but you can also just do it this way with a counterexample. So is that clear? Okay.
Okay, I'm so sorry. I still didn't understand this. Can you just explain a little more?
Right, yeah. So we're first trying to see if this is invertible. So we know it's invertible if TV equals B has a unique solution for all B, right? So if you take, right, so we're thinking, well, you want to show it's not invertible, right? So we're going to take the negation of that statement. And the negation of that statement is there exists a B and there exists a T, or B, there exists a V, there exist B's and there exists a B such that TV equals B has two solutions, right? So if we can just find some B that TV equals B has more than one solution, right? Or no solution, then we've shown it's not invertible, right? So essentially we're giving a counterexample, right? We're trying to show that it's not invertible. So we show that it violates this condition. Is that clear?
Yeah, that's clear. And how are we choosing B?
V, yeah. So we're sort of just choosing it so that it equals to our term B. If you're asking how do we find our term V, there really isn't much of a better way than just trying out examples and finding something that works. So it's kind of one of those sort of brute forcey kind of questions where you just try to look for counterexamples and try to see like what will violate the condition. What are the two solutions? Yeah, so the two solutions, so we'll call this V1. So this is our first solution. So 1, 0, 0, 0. And we'll call this V2. So the two solutions are our vectors 0, -1, -1, -1, and 1, 0, 0, 0, 0. And we see that these are not equal vectors. So B does not have a unique solution. So our transformation is not invertible. Is that clear?
Yep.
Great, awesome. Okay. Right, so we know our T isn't invertible, so because there's a non-unique solution. Right, so now for the harder task, finding the eigenvalues. So this is a little bit of an abstract function definition, so we can't really compute them directly. What we can do, however, and what we like to do in these types of questions is sort of investigate the properties of our functions. We want to see, okay, if V is an eigenvector, right? And what would its eigenvalue look like, right? So we're going to consider an arbitrary eigenvector V with eigenvalue lambda of T. And we're going to sort of investigate, right? We're going to see, okay, what will the lambda look like, right? And we know, again, we know this exists. Every transformation or matrix will have at least one eigenvalue, right? All right, so we know that T of V sends V to lambda of V, right? And we know that lambda of V, well, she's equal to lambda V1, lambda V2, and lambda Vn. But, right, we also know by definition of T of V sends V to this, right? So we have this sort of equality over here because we know by definition of our function, it will send V to this, right? But we know it will also send V to this because, well, V is an eigenvector, right? Is that clear? I know this is a little confusing, so, but is this equality clear? Because this is just by the definition of the function, whereas this is by the fact that it's an eigenvector. Is that clear?
So it's based on the assumption that T has V as the eigenvector and eigenvalue.
Yeah. Yeah, there is always at least one eigenvalue. Yeah. So we're assuming that V is an arbitrary eigenvector with eigenvalue lambda, right? Yeah. And we know that this exists because it will have at least one. Is that clear? Okay. Great. So I'm gonna go on. Right? So we know that the equality of these two vectors, well, we know if two vectors are equal, then each of their components must be equal. So this equals that, this equals that, this equals that, right? And we get something interesting, right? We get these, right? So we get lambda V1 is equal to V2 minus V1, right? Up here. And we can sort of rearrange this. So we can, I guess we'll draw this to make it more explicit. We'll bring the V1 over here, and the V2 over here, I'll bring the Vn over here, right? And you can factor the scalars, right? And you get these equalities. So I think some of us might be noticing a pattern here, and you'd be right? You're sort of noticing a pattern like V2 is equal to 1 plus lambda V1, V3 is equal to 1 plus lambda V2, and so on and so forth, back up to V1. How do we know it is not invertible? Oh, yeah, so we knew it wasn't invertible because we showed a counterexample, right? Okay, right? So we're going to investigate this pattern farther because in mathematics, when you see a pattern, you take that and you run, right? We like patterns in mathematics. They're very nice. But like looking at the question, how did you know? I mean, I sort of just brute forced cases until I found one that violated it. I mean, there isn't really like a super, yeah, of course. I can go back. Yeah. I know this is a bit.
You can give another example of B. I mean,
right.
after
you don't have to choose, so you don't have to, okay, yeah. So I can give another example after, but yeah, you don't have to choose a specific B. It's just, yeah, okay. Well, let's continue onwards. Right, so we'll investigate this pattern farther, okay? So we know that V3, right, is equal to lambda 1 plus lambda V2, right, from our pattern up here, right? Oh, but what do we know V2 is equal? We know that V2 is equal to 1 plus lambda V1, right? And well, this times this, that's just 1 plus lambda squared V1, right? And we can sort of apply this inductively, I guess you could sort of say. The brackets are really bad here, so ignore that, but it should be like this, right? It's the same idea, right? We know V4 is equal to 1 plus lambda V3, right? And we know that V3 is equal to 1 plus lambda V2, that's squared, they're all -1. Yeah, so we're gonna see that, but let's continue, right? We see a pattern again, so yeah. So if we apply this same pattern all the way up to V1, right, what we get is V1 is equal to 1 plus lambda to the power of n, because we did it n times. We started at V3 and we went all the way up to V1, right? We'll have V1 is equal to 1 plus lambda V1, right? So we know if these are equal, right? We know the vectors are equal. So that means the scalars must also be equal as well, right? Right, so the scalar quantities, so you can sort of think of in a phantom one being here, right? So sort of an imaginary one that's just sort of in the background, right, is right there, right? Right, so we know that 1 is equal to 1 plus lambda to the power of n because, well, the two vectors are equal. So the only possibility is that the scalars must be equal, right? If we take the nth root of this, so the nth root denoted like this, it's also equivalent to or 1 over n. You might consider something in there, right? What we get is 1 to the power of 1 over n, right? Because we know that the nth root is just putting something to the power of 1 over n. And yes, as Ethan said, we're going to show that they're not equal to 0 as well, right? We get 1 to the power of 1 over n. That's equal to 1 plus lambda, right? Right? Right. So we're going to be using Euler's identity, right? So we're going to be using his famous identity. It's actually technically e to the pi I, but the 2 here, we'll be using it with the 2 here, but it's the same idea, right? E to the I times the multiple of pi, that's equal to 1. Right? Yeah, and there's Euler. Right. Okay. And with this identity, our equality becomes, right, lambda is equal to e to the I times 2 pi 1 over n, right, minus 1, right? Because we had, let's just go back to before, right? We had this equality, right? 1 over n, right? So we have our equality becomes e to the I 2 pi times 1 over n minus 1 is equal to lambda, right? Great. And we need n solutions in the complex plane by the fundamental theorem of algebra. And we know that if we multiply 1 by any multiple of k, right, what we're getting is simply, right, our kth eigenvalue, lambda k, is equal to e to the I 2 pi times k over n minus 1, right? Yeah, so that's very beautiful. That's very nice. So I'm actually going to go over one more thing because there is one more thing we have to cover. So we know that lambda cannot, or our eigenvalue cannot equal 0, because if it did, right, well, if v1 equals 0, right, then v2 must equal 0, and they all must equal 0, because again, they're all equal to each other. v4 is equal to 1 plus lambda v3, and then v3 is equal to 1 plus lambda v2, right? And because if one of them equals 0, they all equal 0. So that means that none of the v's can equal 0. So we know for sure that none of these equal 0. I have no idea how we're ever supposed to be able to do this by reading the textbook and attending a lecture. I don't know. I don't really know how the course is taught, so I can't really comment on that. I'm sorry. Yeah, so basically we have that this is equal to 1, right? So this is equal to 1, right? Well, if we multiply 1 by k, right, or k over n, we have this is still equal, right? Is that clear to everybody? I know this is a bit confusing. But yeah, like that's the gist of it, right? But hopefully this is clear to everybody. I don't think you'll get something like this difficult on the, I don't think you'll get something that this difficult on the exam. As in regards to course difficulty, I don't think, I mean, it's all about practice, but I don't know. I don't know like what the materials in the course are or anything, so I can't speak about that. So we are at time, but I'm going to continue this. We only got one more question left. And if anyone wants to go, they can. So I know people have other things they need to do. Yeah. All right, so, well, yeah, and I just want to say, I didn't come into H1 knowing anything either. I think it is about doing the practice exercises and getting experience with proofs, but yeah, I can't really comment on the difficulty this year, but I'm not gonna waste time on that. Yeah, that's the answer for Q5. Yeah, I'm right. Okay, so we're gonna for question 6, we're gonna let A be a square matrix with 2 properties, right? So all of its entries are non-negative, right? And the sum of each of its rows, right? So the sum of each of its rows equals 1, right? So we're going to want to demonstrate 2 facts here, right? So the matrix must have 1 eigenvalue, that's 1, and that all of its eigenvalues, the absolute value of all of its eigenvalues, are less than or equal to 1, right? So for all eigenvalues for this matrix, we have that their absolute values are less than or equal to 1. Great, so let's get into this. So we're going to consider the vector 1, 1 all the way up to 1, right? So this will be our vector. And what we're going to show is we're going to show this is an eigenvector of our matrix A, and that it has eigenvalue 1. Okay, let's do this. Right. Oh, yep, of course. I know I'm speeding through this a bit. We are over time, so I don't want to waste anyone's time too much. So, right, so this is the question. Is that clear? Is the question clear or? Okay. Okay, great. So we're going to consider the vector 1, 1 all the way up to 1, which is the nth component, right? And we notice by definition of matrix vector multiplication, right? The ith component of AB must be given by this sum. So I know this is a bit scary looking, so I'm just going to explain it. So we'll consider like some ith row of, right? So we have something like A1, AI2, AIN, right? Something like this. And if we multiply, right, some vector, right, V1, V2, right? Yep. Times some vector like V, right? Well, we know that the ith component, right? The ith component of this vector is just going to be equal to, okay, let me look here. Okay. Oh yeah, okay. Yeah. So right. So we know that this is going to be equal to, right? Right, the ith component. So we're thinking this is the ith spot, it's the ith row, right? Row, right, is equal to AI1 times V1 plus AI2 V2, and right, all the way up to AIN Vn, right? So that's our ith component of of AV, right? And so I'll just note this is a vector. Is a vector, right? Right. We know its ith component is equal to this, right? By our definitions. So is that clear? I know this is like a little, like quite a bit. So if anyone's confused about this, just let me know. Okay, great. So we also know that, well, by definition of V, right, every component is 1. So we have that this is simply just equal to the sum of AIK. And recall, we're given that the sum of each row of our matrix is equal to 1, right? So we get this equality. So every entry of our AVI, right? Every entry of our AV is simply equal to 1, right? Dominant eigenvalue. Yeah, exactly. We're showing that, right? Right, so we know that AVI, the ith component of AV, is always going to be equal to 1. Well, what we just did is we sent V to 1 times V, which is just V, right? So we see that it's sent to 1, right? 1 times itself. So that means lambda equals 1 by definition is an eigenvalue for a matrix. So that's awesome. We showed what we wanted to get. So that's great. Okay, is that clear to everybody? Just yeah. Okay. Right. So we're going to show the second fact now. This is a little more difficult. For any eigenvalue lambda with eigenvector v, we have the absolute value of lambda is less than or equal to 1. So we're going to show this fact. Yeah, and yeah, I know. I know that. Oh, could you explain the last part again? Yeah, I can explain the last part. Let me go back up. Right. So we know that for AV, right, the ith components, the ith parts, you can think of like if this is a vector, right? We have the ith component is like right here, right? We know that this ith component is equal to 1. And this is true for like all the components. So that means that this vector is just sent to itself, right? Because we have 1, 1, 1, and we sent that to, right? So we think we sent that, so AV sends that to 1, 1, 1. So we send that through A to 1, 1, 1, and that's just 1 times itself, right? So we know, right, that the eigenvalues are just the scalars that the matrix sends the vectors to, right? Sends our eigenvectors to. Is that clear? Okay, I'm going to go on because, yeah, we need to finish up because we're at time, right? Yeah, so we know that for any eigenvalue lambda with eigenvector v, we have the absolute value of lambda is less than or equal to 1. And yes, everything will be posted, don't worry. I'll post the recording and I'll post the slides, so don't worry about that, right? So we're going to sort of just consider the maximum absolute value of the components of our vector. Don't worry too much about this. It's going to come up later, but right. So this will just be a useful notion for us. So just think of the absolute value VR. This is the maximum of all the stuff in our vector, right? All the stuff in our eigenvector, this is the maximum absolute value. Oh, when will everything be posted? Probably soon once the recording's finished. Once the recording has finished processing, right? So we're going to investigate the components of the absolute value of AV. And right, we see that, right? So for the ith component of AV, right, again, by the same definition we used earlier, we have that this is simply equal to this sum. Hopefully that's clear. Yeah. So this is just the same definition we used above, right? So same stuff. So we're going to use our friend the triangle inequality. You've probably used them in A31, and if you decide to take B43, you'll use a lot of them there too. So we're going to use the triangle inequality, and we get that, well, this is less than or equal to, the absolute value of the sum is less than or equal to the sum of the absolute values, right? And this follows from the triangle inequality. So if you have A plus B plus C, this is less than or equal to A plus B plus C, right? By triangle, so triangle inequality. So hopefully everyone is at least somewhat familiar with the triangle inequality, right? Right, so we're also going to recall that the absolute value of the product is the absolute value of the product is the product of the absolute value. So basically what this is saying is that if we have a B, that's equal to a B, right? And we get, right, that these two are equal, right? Right, so we're going to choose the maximum, sorry, that should be absolute value, but it's the same idea, right? Right? We have, right, so for the absolute value VR, right, which is just the max of this set, right, we're taking the maximum of all the absolute values in our eigenvector, right? Well, we know obviously if we take the maximum, right, and we sum over that, that's going to be less than or equal to, right, just this. Is that clear to everybody? Right? So we have, this is less than or equal to that because this is the maximum over all of these, right? So we consider this is the set of all the absolute values of the components of our eigenvector. Well, right, this value is just the maximum of that. So it's the biggest possible value we can get. And we know this exists because it's a finite set, right? And we know that the absolute value of our biggest component is constant with respect to our sum, right? And you might know from A37, you can pull out constants from the sum, right? It's constant, right? We picked one, we fixed it. So we can pull it out of our sums, right? And what we get is that the absolute value, this is just equal to, well, this pulled out, right? Because this is constant with respect to our sum, right? How do we deal though? How do we deal with like this, right? Because we still have this awkward absolute value here. We're so close to using our given information, but let's recall, right? We know that all components of our matrix are greater than 0, right? Or greater than or equal to, right? So we know we can remove the absolute value because it's redundant, right? If all the components are greater than or equal to 0, then we know that, well, the absolute value of all those terms are just the terms themselves because they're all greater than or equal to 0, right? And we know, right, from our other piece of given information, this is nothing but 1, right? Oh yeah, can I scroll up? Yeah, sure. Right here, right? Okay, good. All right. Okay. So we know that the ith component of AVI, the absolute value of the ith component of AVI is less than or equal to the absolute value of the maximum, maximum absolute value of our eigenvector, right? So we can easily, we can choose I to be our rth component, right? So choose the component that's the same as our maximum, the component that gives the maximum absolute value, right? And well, this just gives us, right, the rth component of AV is equal to lambda VR because, right, this is an eigenvalue, this is an eigenvector. We supposed V was an eigenvector, right? And again, we have the property that A, absolute value of AB is equal to A, B, right? We have that this is equal to that. And right, we already proved that this component, right, is less than or equal to VR, right? Right? So we also know we should note that VR cannot equal 0 because that would mean the maximum of any absolute value of our vector would be 0, right? Because we're considering the maximum of the absolute value. So if the maximum of the absolute values is 0, that means all our components are 0, right? And we don't consider 0 vectors eigenvectors, right? So VR cannot equal 0. So therefore, we may divide by the absolute value of VR, right? So just so we know that this is legal, right? And we get, right, by dividing, right? So we divide both sides by VR, right? Divide both sides by that. We get the equality, absolute value of lambda is less than or equal to 1. And that's what we wanted, right? That's basically what we wanted to show. And that is the last of all the questions. So I apologize, we did go a little over time, but I want to thank you all for coming. I want to thank all the people who posted solutions on Piazza. Those were very helpful for planning this review seminar. And if you have any questions or any feedback, like feel free to, yep, go right ahead, go right ahead.
I have a question about question 5, the last slide in question 5.
Yep. Yeah, I can scroll back up. 1 second. Okay, sorry. They're pretty long, so yep.
How was the last slide in question 5, the one which ended the proof?
Yeah, this is the one that ended the proof for question 5.
Oh wait, question 6, sorry. Question 6.
Oh, question 6. Yeah, of course. Yeah, I know this is a pretty long question, so. Yeah, okay, here we go. right? Here's where we ended.
Also, Alex, if you can go over question 6, part A again, just a quick recap of it.
Yeah, of course, I can do that. So, okay. Okay, so let's scroll back up to question 8. Wait, so I'm gonna go back up to where we hit that. Right, so what we did was, right, I should scroll down. Okay, so what we did is we chose the vector v, and that's just the vector with one as all its components, right? And we're sort of looking, okay, what is the ith component of AVI, right? Well, we know by definition of matrix vector multiplication, right? That's just the first component of V times the first component of the row we're looking at, the ith row, right? Times, yeah, the sum of all those basically. I could write that out if you're not clear on that, but we know that, well, by definition, each component of V is equal to 1. So 1 times anything is just gives back that thing. And we know from supposition that the sum of these is just equal to 1, right? We were given that by the question. So that's basically how we, oh, yeah.
Okay, yeah, I get it. Thank you.
Okay, no problem.
Why do you consider a vector here?
Right, yeah. So we're trying to show that lambda equals 1 is an eigenvalue of our matrix. And this, for lack of a better explanation, this is just the most convenient vector for showing that this is true, right? Because we know if we can show for some vector, A sends it to a multiple of itself, right? Then that vector is an eigenvector, right? With that eigenvalue by definition. Does that make sense? So,
yeah.
Sorry, I know I should have given a better explanation, but that's all I can really say. It's just convenient for the proof.
Yeah, and we get this column vector V from the second property given in the question, right?
So no, so we chose this. So we just chose it, right? This isn't really given to us. We just chose a vector and we showed that vector is an eigenvector with eigenvalue 1, right? So we weren't really given this vector. We kind of just chose it. I know this sounds a little arbitrary, but like all we need to do is show that there is a vector that is sent to a multiple 1 times itself through A.
Okay, so what do we comprehend from the second property given in the question?
Right, yeah. So we don't actually use that property at all in the first part, but we do use the property in the second part, right? And we use this property, right? So we have, let me scroll down for a bit. Right, so we have this absolute value of AIK, and we sort of wanted to get rid of that. And the way we got rid of that is we use the second property, right, that all its components are greater than or equal to 0 to get rid of the absolute value. Because you know the absolute value of any number greater than or equal to 0, right, is just, well, it just gives back that term, right?
Yeah, well, the one that we use in part B, isn't that the first property?
Oh yeah, that is the first property. Yep, you're correct.
Yeah.
Yeah, so we do use the second property in part A. And this is where we use it, right? So right here, right? Because this is just the sum over a single row. And we know that's equal to 1, right? By the second property.
Yeah, got it.
Okay.
Thank you, man. Thank you so much.
No problem. If you have any other questions, like feel free to ask them. All yours right now. So.
Also about question 5, part A,
Yep.
we're talking about B. If you can give another example of if we have to choose any other
Oh
B.
yeah, I think Ethan gave an example of 0, 0. I could go over 1. Yeah, okay. So we could choose, let's see. So we have, okay. So we can consider 0, B equals 0, 0, right? Like this. We can consider this, right? And then we know, right? Tx2, so, okay, let's consider solutions to this, right? So we could consider x2 minus x1, yeah. So we can consider t1, 0, 0, all the way up to 1, right?
Okay. Yeah, I got it. So
Okay.
if we take like 0, 0, 0, and then we can take 1, 1, 1. So they will both give us so the same answers, though it wouldn't be unique.
Yeah. You want
Yes,
you want to
that's
show
how
that just for this value, right? You can pick two V's that when sent through T give you the same value. Then it's not unique, right? Because you can find it different ways.
Yeah, so then we can prove it is invertible.
Then you can show it isn't invertible, right? So we're trying to show it's not invertible.
Yeah.
Okay,
Thanks, man.
great, awesome. Yeah, no problem. And Luke, you can go ahead.
Could you go over the logic of question for part B?
Yeah, I
I'm
can go over that.
a bit confused.
Yeah. Sorry, let me just skip to it. 1 second. Okay, yeah. So here we go. So, yep. Okay, so, all right. I guess I'll just go through it, and you just tell me like the part you're confused at. So, we consider for V, right, that we're just going to say that the absolute value of VR, this is some component of V. This is the maximum of all the absolute values of the components of V. Right? That's a mouthful, but basically what we're saying is it's the maximum of the absolute values of like every single component, right? So we're gonna see, right, we're gonna investigate the components of the absolute value of the ith component of the absolute value of AB, right? So the absolute value of the ith component of this vector. So this is a vector, right? And we're just using our same definition of matrix vector multiplication from the last part of this question. So we know this, we know we have this equality. This is clear, right?
Yeah.
Okay. Right. So, right, we use the triangle inequality. And yeah, you know how the triangle inequality works, right? Okay, so we get this, right? Yeah. Yes, we have product of the absolute values is the absolute value of the product. So this is equal, right? You just broke it up. Right? And we know that the absolute value VR, that's just our maximum. So it's the maximum over all of these, right? We have this inequality, right? So we know that this is bounded, right? And we know that, well, this is just a fixed value, right? So this doesn't change if we change K, right? So we can factor it out, right? So we can factor it out. And the only thing now we have to deal with is this value, right? And we know that all the components are non-negative. So we have that the absolute values of all of these, you can just take them off, right? Because the absolute value of a non-negative number is just that number, right?
Yeah.
And we use the same given information. We use last question. This is equal to 1, right? Because sum of all the rows is 1, right?
Yeah.
Right. So we have this bound now, right? We worked down from here to here, right? Right. And we look at a specific case of this now. So we look at the specific case of when I is equal to R, right? And we know that this equality holds for all R. So if we choose I to equal R, this will still hold. So we have that the absolute value of AV, the rth component of that, well, that's just equal to lambda VR because, well, V is an eigenvalue. So we think if we send AV, we get lambda V, which is just lambda times all of these components, right? So this is just equal to that. And we can split them again. And we know, right?
Now I got it.
Okay, awesome.
I got it.
Yep.
And question 4, part B. Could you explain that?
Yeah, of course. Let me just go back up there. Part B. Oh yeah, okay. So right. So we know that A is a square matrix, and we want to show for sufficiently small epsilon, the matrix A minus epsilon times identity is invertible. So right. Right. So we know where we're going to consider lambda to be an eigenvalue of A with the eigenvector V, right? And we know at least one must exist, right? Because fundamental theorem of algebra, right? And then we're going to note that, well, this product, right, is equal to this, right? That's clear. We then note, right, that, distributes, we get this, and we can factor the scalars out, right? right? So then we also we have to prove that if lambda minus epsilon is an eigenvalue of A, then or A minus epsilon I, then lambda must be an eigenvalue of A, right? So we need to show the F and only F. So we need to show we can go back and forth, right?
Okay.
Yeah. We
So
want to
only
prove
when only when that lambda is the eigenvalue, this equation
Yep.
Okay.
Yep. Well, we used the contrapositive to prove this, and it was basically the same idea as what we did on top, right? Except we showed they're not equal, right? So we know that basically all the eigenvalues of A minus epsilon I are just the eigenvalues of A shifted over by epsilon, right? Right, okay, yeah.
Could you repeat that?
Yeah, so we basically know that the eigenvalues of this matrix right here
Yeah.
are just the eigenvalues of A shifted over by epsilon.
Yeah.
So minus epsilon, yeah. And we know, right, let's say all the lambda i's minus epsilon, let's say all the lambda i's are negative. Then since epsilon is greater than 0, then obviously that's going to be negative as well. So it's going to be less than 0, right? So then we know by our determinant theorem of eigenvalues, right, that's not going to equal 0 because you take a bunch of non-zero numbers and you multiply them together. Well, it's not going to equal 0 still, right? And we say, okay, let's say there is a positive eigenvector, right? So then we just choose the minimum of those positive eigenvectors, right? And we just pick small enough epsilon such that the epsilon minus this minimum is still greater than 0, right? And we can always pick one, right? We can always make epsilon small enough, right? And then we sort of get this inequality, right? These are the ones that are less than 0, but yeah. I'll just erase that, but it's the same idea, right? And we still get this, right? We still get this, right? So it's the same idea as above. We just considered a minimum, right? So we could pick sufficiently small epsilon. Is that clear?
Yeah, and Kaidi actually solved this question using like for the characteristic polynomial of lambda, and the lambda is shifted by epsilon. And what I'm basically understanding is that for whatever lambda, there will always be an epsilon that is small enough to fit the requirements of this question.
Yeah,
right?
Exactly. You can just pick an epsilon small enough so that that's still going to be non-zero. So you can basically make it small enough so that it's not going to make your lambda I equal 0, basically. Yeah.
And question 5 part B, please. Question 5.
Question 5 part B. Yeah, of course. Okay. Right. Okay. So. Right, we considered an arbitrary eigenvector v with eigenvalue lambda p, right? And we investigated. So we know.
Yeah, I understand this part.
Yeah, okay. Yeah. So we have this, right? So we have all these, right?
Yeah.
These are equal, so we carry this stuff over, right? And we have a pattern. So we know that V3, right, is equal to 1 plus lambda V2. Well, and V2 is just equal to 1 plus lambda V1. So we sort of apply that recursively.
Yeah.
So you can sort of think of it as like a recurrence relation, right? And we multiply these two together, we get 1 plus lambda squared V1, right?
Yeah.
And it's sort of the same idea here, right? We're just doing the same thing, but one more time, right? And we know, right, if we do this all the way back to V1, we'll get this, right? It's just applying the pattern over and over and over again.
Mm-hmm.
Right? So we know V1 is equal to V1, right? That's pretty. Yeah. So the only possibility is that our scalars must be equal. So we know that 1 is equal to 1 plus lambda to the power of n, right?
Yeah.
And we can take the nth square root of this, right? And we get this, right? We get this equality.
Yeah.
Okay. And we know by Euler's we know by Euler's identity, 1 is equal to e to the I 2 pi, right?
Yes.
So we can just take 1 and we replace it with e to the I 2 pi. Okay. So with this identity, we get this equality, right?
Yes.
And so the reason why I can also multiply by k here is we have that, well, 1 to the power of 1 over n, right? That's just equal to 1, right? So
Yeah.
we can also multiply by k to the n, and we still maintain our equality, right?
Yeah.
So we can just do any power of k here, essentially up to n, right? And we need n solutions, right? So we can just express this like so, right? For each eigenvalue, it's equal to e to the I 2 pi times k over n minus 1, right?
Yeah, by the way, what is the fundamental theorem of algebra? I haven't learned this in A30. I'm not A31.
Right. Yeah. So I don't know if it's covered in A31. I saw that someone used it in their solution. I didn't know if Kadi covered it or not. But basically, if I have a polynomial, right? Let's say
In
it's
degree
like,
polynomial, we have n solutions.
yeah, n solutions in the complex plane. So there are n numbers in the complex plane that will
Okay, I got it.
satisfy. Okay, great. Yeah, so I'm actually, if nobody else has anything to ask, I'm probably gonna head out now. But I thank everyone for coming. This will be recorded, and the recording will be uploaded. I can't say when exactly, but once it's finished processing, I will upload it, and I will upload the slides as well with the annotations. So yeah.
Thank you, man. It was really helpful.
Oh,
Thank you.
thank you. Yeah, no problem. Yeah.
Thank
Okay.
you. Bye.
I'm gonna stop sharing now. So I will see you all later.
Okay, I'll check them. Thanks.